Right? So entropy is just the expected value of the information. Then we talked about mutual information. And we just learned that mutual information is a function of two random variables. It is measured in the same units as entropy, namely bits. And it captures the essence of it, the intuition behind it is it captures the amount of information that knowing the value of one of the random variable tells you about the other random variable. It's a function of the joint distribution of these two random variables. And it is zero only if the joint distribution is such that they are independent. If and only if they're independent. What's an upper bound on the mutual information between x and y? You think of an upper bound? Let's see, x and y are 2 bits, and they have some joint distribution of the 4 possible values, 0, 0, 0, 1, 1, 0, 1, 1. What's the most that the mutual information can be?
The size of the smallest.
The size of the smallest?
Yeah.
Smallest what?
Information.
Okay, I'm missing the right word there. What did I hear? A little louder? Entropy. Okay. The mutual information between x and y cannot be higher than the entropy of x or the entropy of y. Right? It cannot be higher than the entropy of x, and it cannot be higher than the entropy of y. Because x cannot tell you about y more than is unknown about y. If you think about the entropy of y as the uncertainty surrounding y, then the most x can tell you is bring that uncertainty to 0. It cannot tell you more than that. So mutual information between x and y is greater or equal 0. 0 if and only if they're independent. And smaller or equal h of x, and also smaller or equal h of y, so I can write it as a minimum between h of x and h of y. This is the computer scientist in me writing it that way. In what way is h of x and y, mutual information between x and y different than the mutual information between y and x? What's the difference? What's the relationship? Sorry? They're the same. They're exactly the same. It's a symmetric measure. But the intuition could be a little different. In one case, x tells us about y, and the other y tells us about x. And x and y can be very, very different. X can have 1 bit of information or even less, and y can have huge amount of information in it. So, example. X could be a random variable which is a number chosen between 1 and 1,000,000 with time distribution, uniform or not. Y could be whether that number is even or odd. What's the mutual information between x and y? Y?
Y is 1 bit.
Okay, y is 1 bit, and therefore, first of all, how do you know that y is 1 bit? Is y 1 bit? You're right overall. I just tricked you a little. I didn't tell you that the distribution was uniform. Right? But still you know that y is no more than 1 bit. Right? So y is whether the number is even or odd. There are only 2 outcomes, therefore the information content cannot be more than 1 bit. It would be 1 bit if they were equally likely, even and odd. It would be less than 1 bit if they were not equally likely. Right? Other than that little trick, you're right. So let's say you chose uniformly a number between 1 and 1,000,000. There are exactly as many even numbers as there are odd numbers. So y, being whether they're even or odd, is a 50-50 bit. It has 1 bit of information. Okay, so X was chosen uniformly from 1 to 1,000,000. Y is defined as 1 if X is even, 0 otherwise. Mutual information between X and Y, or let's start before mutual information between X and Y. Entropy of X is, somebody loud? What's the entropy of X? Log? 6 log 10. I'll write it as log of 1,000,000, which is the same as 6 times log of 10. It's a large number. Well, larger than 1. What's the entropy of Y? Come on, say it out loud. It's all right. What's the entropy of Y? Y has 2 possible outcomes, and they're all equally likely because the uniform distribution over the evens and odds. So 1 bit. So let's actually calculate the number roughly here. What's log base 2 of 10? Somewhere between 3 and 3.5. 3.2 I think is pretty close. 3.2 times 6, 18.2 times 6, 19.2. This is about 19.2 bits. Y has 1 bit. What's the mutual information between X and Y? The first thing you know is that it cannot be less than 0. The second thing you know is that it must be less than the entropy of X and less than the entropy of Y. Right? You cannot have more information, one person telling you about the other than you don't know about the other. So it's bounded by 1 bit. Okay? Now the point that you made, remind me of your name? Tom. The point that Tom made was that knowing, I think you made that point, or at least you intended to make that point, or you were going to, is that knowing X fully gives you Y. If you're told X, if you're told what number was chosen out of 1,000,000, you know with full certainty the value of Y, because you know if it's even or odd. Right? So knowing X always reduces the uncertainty of Y to 0. Another way to write it is that the conditional entropy of Y, given X, under the condition that you know X, is 0. And we define the mutual information as a difference between the conditional entropy and the unconditional entropy. Mutual information between X and Y is the entropy of Y minus the same entropy of Y if we know X. The entropy of Y is 1 bit. The conditional entropy of Y given X is 0. No uncertainty left. And therefore the mutual information is 1 bit. So knowing X tells you everything you need to know about Y. But knowing Y does not tell you everything you need to know about X. It gives you 1 bit. In the case of from X to Y, that 1 bit was everything. In the case of Y to X, that 1 bit is not everything. So now I can tell you that the conditional entropy of X given Y is, what is it? Say it louder, please. Log of 500,000. That's one way of saying it. I want you to do it a different way. 18.2. Yeah, just take what the entropy was before and take away 1 bit. We already know how much X tells us about Y, how much Y tells us about X. That's the beauty of it. They tell us the same amount. So we just take the original entropy of X and subtract from it what Y tells us about X. So there's 18.2. Now, your name please? Yeah. I'm sorry? Dan. The solution that Dan suggested was a little different. It says if you know Y, then you know that it's an even number, let's say, or odd. So if you know it's an even number, there are only 500,000 choices rather than a million choices. So within that limited space, it's log of 500,000. A different way of arriving at the same answer. This, in general, would be an easier way. You can imagine a more complicated distribution where it's easy to calculate this, and therefore it's easy to calculate how much x, x tells us about y, but it may be hard to calculate this directly. So this is a trick you can use, remembering that the entropies of the two sides are not the same, the conditional entropies are not the same. The only thing that's the same is how many bits one variable tells us about the other. So the only thing that's symmetric. Then.
Does the mutual information assistance of the random variable make any, does it satisfy the triangle inequality?
That's an excellent question. So a functional, some kind of a function between two arguments is a distance if it satisfies a set of conditions. It has to be non-negative. It has to be 0 if and only if the two arguments are the same. And there may be some other conditions, but one important condition for proper distances is triangle inequality. Triangle inequality says that if you have, well, in this case, I'm not sure how you would translate this, but it would be, let's say, x, y, and z. Mutual information between x and y plus mutual information between y and z. For the triangle inequality to hold, must be, I'm just writing must be, I'm not claiming that it is, must be greater than mutual information between x and z. Is that what you meant then? So let's draw it. I don't know the answer to your question. I'm trying to figure it out. Here's x. Let's make a bigger drawing somewhere. Here's x. Here's y. Here's z. Mutual information between x and y is this part. Mutual information between y and z is this part, and I already see one problem. They have some overlap. And mutual information between x and z is this part. So if I want to show that this is less than, yeah, I think the answer is no. So I can imagine a situation where these two are 0. There could still be mutual information between x and z. Okay, I think it's fairly easy to come up with an example. Here's an example. X and z are somehow related. Y is totally random, unrelated to anything else. Okay? So since y is totally random, unrelated to anything else, its mutual information with anything would be 0. Okay. I showed you how to depict these things on the board with a caveat. Sometimes our intuition does not agree with, so don't use this as a rigorous proof. But you can use it to help you think. For example, I came up with my answer to your question by drawing this picture and looking at it saying, oh, if these two were 0 and this one was not, then it would contradict triangle inequality. So you can do the same thing. You can use it to help speed up your thinking, come up with ideas, come up with examples. But ultimately, to prove them, you need to go through the definitions of entropy, mutual information, and so forth. Okay, I showed you a picture. But we can use this picture. Maybe I should spend some time going over the meaning of the different parts. So you identify each circle with the amount of entropy or uncertainty for that random variable. And then, because we said information is additive, it is actually measured in bits and kilograms and whatever, something that you can put together. You can think about set operations like union and subtraction and overlap. So the overlap information between, say, x and y is the mutual information between x and y, right? So this area with these north, east, southwest leaning lines is the mutual information between x and y. Now look at this area, the y, after you exclude this part, okay? This moon-shaped thing. What is it? Can somebody tell me? H of y, y given x. Okay? It is kind of minus x. It's h of y when we know x. The way to think about it is if you know x, you already occupy this entire area. You already removed all the uncertainty that's in this circle. And therefore, what are you left with? You're left with the uncertainty of y, the part that was not helped by x. So you can see why this is, it agrees with the picture that this can be calculated as the full entropy of y minus the overlap between the two. Right, that's what we have here. One of these should do that. I'll do it again here. H of y is h of y condition on x is h of y minus mutual information between y and x. Okay, now what about the joint entropy of x and y? Forget about the third circle for a moment. You have two circles with overlap. The joint entropy is the joint uncertainty of the joint distribution of x and y. Last time we had a formula for it. You can just do sum of p of x and y log of 1 over p of x and y, right? You can just think of x and y as a single random variable that takes values in the space, in the Cartesian space of x and y. Cartesian product of x and y. So the joint entropy is this union of space. These two circles together. And one way to break it down is as, entropy of x plus entropy of y. But I'm missing something. What am I missing? I need to make a correction. I have to subtract the intersection. Minus I of x y. So this circle plus this circle minus the intersection, because I counted the intersection twice. This is not a proof. This is just a quick mnemonic. But you can prove it. If you spell out these quantities by their definition, you should be able to prove it with a little bit of algebraic manipulation. Okay, now let's move to all three, x, y, and z. So I need to define for you more rigorously some operators and their preferences, their order of preference or ranking. So you already know this operator. This is the conditioning operator, given. Entropy of y given x, or condition on x. You already know this operator, the semicolon. It separates the two sides of a mutual information. It's mutual information between what's on the left and on the right of the semicolon. I think it should be a colon, not a semicolon, because a colon is more symmetric. Semicolon has some direction to it, but that's what it is. A third operator is the comma operator. So a comma between x and y is effectively a grouping of x and y into a single random variable, which is the Cartesian product of the two. Grouping. So now, let's try this. What is h of x, comma, y given z? You might think, well, which operator do you apply first? And the answer is you apply comma always first. So this is the same as putting these in brackets. So I'm asking you about the entropy of the joint random variable xy given z. Where would it be in the picture? It would be this two fused circles in the top. That's the joint entropy of x and y. But then given z means we have to exclude this part that z takes out. So if I had color, which I do, it would be this part. Okay, now compare that to h of x given y comma z. Again, sorry about that, I'll try to stay up. Again, the comma comes first. So it is as if you put the angled brackets here. Now you're thinking of y and z as a single fused variable. And you're asking yourself, what is the amount of entropy in x if we know y and z? So y and z tell us everything they can tell us about x. What's the remaining uncertainty? Okay, who wants to tell me that? What would it be in the picture? H of x given y and z. Somebody who hasn't spoken yet today?
It would be just the portion of x which isn't overlapping anything.
Thank you. It'll be this. Okay? I took all of x and I took out anything that was in y or z or both. Okay, where can I write it would be more visible to everybody? What is this? Mutual information between x, semicolon, and y given z. So the rule here is that this is the next operator to be applied. So these are close together. So first we interpret everything relative to dependence. There's really no other coherent way of interpreting this. We interpret everything conditioned on z. So if you think of the definition of x and y, definition of x and y is h of x I'll write it like this, minus h of x given y. So if the dependence on z didn't exist, mutual information between x and y is just h of x minus h of x given y. Okay, we know that. Now we add in the dependence on z everywhere. So what we're saying is we're looking at how much information x tells us on average about y in a world where z is always known. Okay, that's the way to think about it. It's not in the world where z is always the same. Z may be different at different times, but it is always known. In the world where z is always known, how much information does x tell us on average about y? So I will add the dependence on z here and here. Now, how can I relate it to the picture? I need more colors. What's the first thing? Entropy of x given z. That's x subtracting away this part. So it'll be purple. What's the second part? Entropy of x given y and z. We already did that. That's the blue. That's all of x after taking away both what y tells us and what z tells us. So it's the purple minus the blue. So it ends up being this part. So another way of thinking about it is by going back here and saying it's the mutual information between x and y, but subtract away everything that z tells us. Mutual information between x and y is this whole thing, but I take away the part that z tells us. That's why I said there's only one way of understanding this. Okay, so now let's define, to make things complicated, let's define mutual information between the three variables, I, x, semicolon, y, semicolon, z. Now this is not defined until now. Nothing in what I told you should determine for you what this means. We have to decide what it means now. How should we define it? Well, one good property is that it should be symmetric with regard to any permutation of x, y, and z. Right? This is in the spirit of mutual information. But that still doesn't fully determine it. Here's how it's normally defined. It's defined as the joint entropy of x, y, and z minus the joint entropy of all the pairs, x, y minus h, y, z minus h, x, z, plus the entropy of each one of the individual, h of x plus h of y plus h of z. If you're familiar with the inclusion-exclusion principle, there's a famous problems in computer science with secretaries stuffing envelopes. Does that ring a bell? It looks familiar. It's the full set minus all the pairways interactions. This is like the full intersection minus all the pairways intersections plus all the single intersections, namely the individuals. Or you can think about it the other way around. It's all the circles minus all the pairwise intersection of the circles plus all the three-ways intersection of the circles. And if we had more, if we had 4 or 5 or 6, you would keep alternating the sign.
Is that a semicolon in between the x and the y?
Here?
Yeah,
no, here it's not. Here it is. These are semicolons. I believe it should be a colon, but it's normally they use a semicolon. Now, what is the interpretation of this? Well, you can think about it really hard. Let me give you what it is equal to, among other things. It is equal to I of x semicolon y minus I of x semicolon y given z. First of all, you can tell from the original definition that it's symmetric with regard to x, y, and z. If you permuted who is x, who is y, who is z, you'd get the same number, right? It is independent of order. And therefore, if you believe me that it's true for this, then it's true for all other formulas that replace, this could be z and y, and this could, x and y. Any way of renaming the x, y, and z should work. So x and y and z, take them as just any order of the three. What does this mean? It's the mutual information between two variables minus the mutual information between two variables if the third one is known. It's the difference between the conditional mutual information and the unconditional mutual information. So another way of thinking about it, if you remember that the difference between, compare that to difference between entropy of a variable minus the conditional entropy of a variable. It looks a little bit like this, right? We define this as the mutual information between A and B. The difference between what is unknown about A versus what's unknown about A when you know B. Well, here it's a little bit different. Mutual information between two variables minus mutual information between them when you know the third one. This little difference is important. But let's first identify this quantity over there. So anybody knows where in this picture of circles the three-way mutual information is? There's only one place it could be, really. I'm sorry?
The common of the three circles.
The intersection of all three. It's this part. You can get to that from this formula. If you take all three circles, then subtract from them all pairwise intersections, it turns out that you will have subtracted this 3 times. I'm sorry. You've subtracted it 3 times. All circles. So this you will take away once, but this you will take away this is, if you take this point, it's included in h of x, this is x, this is z, h of z, also h of x and z, and also h of x, y, and z. So it's included twice with a positive, 3 times with a positive sign, and once with a negative sign. I'm sorry? This formula? Yeah. You may be right. So did I get it wrong here? Let me derive it from here and I'll figure out my confusion later. This is mutual information between x and y minus their mutual information given z. Mutual information between x and y is this big yellow thing, and the part given c is just this part, and therefore we're left with this part. Now here's where intuition breaks down. Mutual information between 3 random variables can be negative, whereas mutual information between 2 random variables can never be negative. So this is where I warned you about relying too much on the picture. In the picture, area can never be negative. So the picture is not a perfect model of what's happening. Here, you can see perhaps why it could be negative, why it could be that this is larger than this. It could be that X and Y really don't tell you anything about each other. But when Z is known, they do tell you stuff about each other. Right? That's entirely possible. That X and Y are useless with regard to each other. They don't tell you anything about each other. Except if you know something else, all of a sudden they become very useful. You can think about a jigsaw puzzle. You have pieces. You don't know how to put them together. But all of a sudden somebody gives you a clue, and all of a sudden these pieces become useful. So if that's the case, this becomes bigger than this, and therefore this is negative. There's something wrong with this.
You switch the positive and negative sign?
Maybe. Maybe that's what I did. So figure it out on your own. I'll figure it out on my own. We'll compare notes next time. So I don't take too much time. Please.
What does negative information mean? Like, if it's negative, intuitively, what would that mean?
Okay, so that's a fair question. If we call it information, then how can it be negative? And the answer is maybe we shouldn't call it information. We call it mutual information between three random variables, and we define it as the difference between the mutual information of two of them under the condition that the third is known or not known. So in other words, we're saying, do X and Y tell us more about each other when Z is known and when Z is not known? And the answer is sometimes they tell us more under this condition, sometimes under that condition. So the difference between the two maybe should not be called information really. Maybe it should be called difference in mutual information. But the interesting thing about it is it's symmetric. If you commute the values of X, Y, and Z, you'd get the same number for the same overall distribution. So there is something invariant there. There's something, perhaps there's a simpler intuition that is invariant under the X, Y, and Z, rather than thinking about it this way. I do know that three-way mutual information is this intersection. So what I suspect is wrong is this formula. Get you what?
The entropy of X and Y, the entropy of Y and Z, doesn't it offset the area in order to know? You just didn't count.
Entropy of X and Y, which is 2.
Turn bottom of the 2x to negative 2.
Oh, I see. Thank you. So I was looking at this point here and I was saying, how many times am I counting this area, right? And you're saying that I'm counting it in H of X, I'm counting it in H of Z, and where else did you say I'm counting it?
Also in H.
Oh, yeah, of course, it's here. Thank you. Okay. So I'm counting it because of Z is here and because X is here. Counting it 3 times negatively. And 3 times positively. So there's nothing wrong with this formula. Thank you. It's just momentary confusion on my part. So, well, I didn't prove there's nothing wrong with this formula, but at least it agrees with that. So this area gets cancelled out because it's counted 3 times positively, 3 times negatively. Thank you. This area should also be cancelled out. Let's see if it does. It's only counted under this. And no, it's also counted under all of them. It's counted under this, it's counted under this, it's counted under this, and it's counted under this. So again, 2 pluses, 2 minuses. Cancels out. And the intersection is in all of them. So it's counted 3 times positively, 3 times negatively, and then 1 time positively. Okay, we restored its honor. This is the right formula. Okay, let's look at one more expression of this type to show you the additivity of mutual information under some conditions. I know I used the eraser. Ah, here it is. Mutual information between x on one hand and y and z on the other. So the first thing to know is that the comma comes first. Comma grabs the two variables on both sides as if you had curly brackets. So it's how much does x tell you about the joint distribution of y and z, or equivalently, how much does the value of y and z, knowing both, tell you about the answer, or how much does it reduce the uncertainty of x? We can break this down into the mutual information between x and y plus the mutual information between x and z given y. So what we did here is, it's a little bit like the chain rule in probability and statistics. Remember the chain rule? Chain rule would tell you that probability of y and z given x is the same as probability of y given x times probability of z given y and x. If this is not immediately clear to you, get rid of the x. Probability of y and z is probability of y times probability of z given y. You break down the prediction of y and z to first predicting y and then predicting z given that you already know y. And that given is important because it changes the probability of y. Okay? And now to go from here to here, you just add the dependence on x. You always know that it all depends on x. So you can always add the dependence on x here, and here, and here. Now why is this the same as this? I wrote it in reverse order. I wrote first the x and then y and z. But really the way I interpreted it is, I'm trying to, let me write it in the other order and maybe it'll be easier to follow. You have y and z here, I'm sorry, y comma z here, in brackets, and then you have x. So you should already know anything with I, with mutual information, you can invert without thinking twice. And I'll invert this one too. This is mutual information between y and x plus mutual information between z and x given y. So you can also invert it here and keep the condition here, because we said this operator is stronger than this one. Or maybe you say this one is stronger, but basically you can leave this here and invert it. This operation applies to everything here. So I think you would say that this operator comes next, actually. Okay, so let's look at this row. It may make more sense. I'm trying to infer something about y and z by knowing x. And I'm asking, how much can I know about y and z by knowing x? How much does x tell me about y and z? And the answer is, it's the same as whatever I can know about y from x plus whatever I can know about z from x, but condition on already knowing y. It's important to condition because knowing y already changes the picture, changes how much I will know here. So in that sense, mutual information is additive. You can think about it as the chain rule of mutual information. You can reduce the uncertainty of something that you're interested in, maybe the classification of your machine learning problem. You have a certain uncertainty before you know anything, and then as you know things, the uncertainty is reduced. And if you have many things that help you reduce it, you can calculate how much each one of them helps you reduce it. But then if you want to calculate how much they all together help you reduce it, it's not the sum of all of them, right? So let's make it very concrete. You're trying to predict some output, y, predict y from some attributes x1, x2 through xn. If you were just trying to calculate the probability, you would say probability of y given x1 through xn. You could write it down. I don't want to do that because there's no direct analogy. Let me just go do the mutual information. Originally, you have some entropy in y. That's based on the prior distribution of possible outputs, possible outcomes. You can think of your job in machine learning, the way we thought about it until now is to make a prediction, an actual prediction. But you can think of yourself as hedging your bets. And instead of making a prediction, just trying to reduce the uncertainty of the answer. Namely, increase the sharpness of the distribution of the answer. If you want to guess if someone is a male or a female based on text communication with them, you know a priori that they are, let's say, equally likely to be male or female. So the uncertainty of your prediction would be 1 bit. Now you start communicating with them and you get some hints. And these hints change your estimate. And maybe at some point you're fairly convinced it's a female. Maybe 90%, 10%. That reduces your uncertainty about who you're communicating with, it's male or female. So instead of at some point stopping and saying, okay, I'm going to guess the most likely one, let's just rephrase how we think of machine learning as reducing the uncertainty in the outcome. Okay? So now you have all these predictors, and you can calculate the mutual information between y and x, each one of these predictors. And if you could only choose one predictor, maybe you want to choose the one that has the highest mutual information. Now if you had two predictors, x1 and x2, it is not true that the two of them together would give you amount of information equal to the sum of how much each one of them will give you alone, because there's some overlap between the information they give you. In general, the mutual information between y and x1 through xn could be written down as the mutual information between y and x1 plus the mutual information between y and y and x2 given x1 plus the mutual information between y and x3 given x1, x2, and so forth. So this is roughly comparable to the chain rule in probability theory. Each one of these components, can they be negative? Can this be negative? I expect everybody to be moving your heads in a certain direction enthusiastically. You're saying it can be negative. Under what conditions?
So big case where x3 doesn't tell you anything about y, but x2 tells you something.
Let's say x3 by itself doesn't tell you anything about y, but with x1 and x2 it does. That would not make it negative. It would make it 0. I'm sorry, it would make it, in this case, it would be positive, and without this it would be 0. So expression of this kind is still regular mutual information between two random variables. It's just conditioned. These are the two random variables between which we're measuring mutual information, and the fact that it's conditioned on something doesn't change the fact that mutual information between two random variables can never be negative. The only case where it can be negative, and I apologize for confusing you with that, is when it's defined as mutual information between three random variables. You have two semicolons in the expression. 1, 2, x, y, z. But we're not dealing with that situation at all here. So each one of these components is still plain old mutual information, albeit conditioned. So this cannot be negative. So the take-home message is if you have many predictors that help you in reducing the uncertainty of the answer, you can add them one at a time. If you do it right, you're guaranteed to never increase your uncertainty. You might decrease it by a lot, you might decrease it by a little, or you might not even decrease it at all. The other thing to notice is that this expression does not depend on the order in which we break it down. Just like the chain rule in probability does not depend on, you can break it down in any order you want, it's still the same expression. Which means if you're going to use, if you know that you're going to use all n predictors, if you do it right, and that's a big if, and if you don't make any other assumptions, but theoretically it doesn't matter in which order you incorporate them into your model. At the end of the day, all of them together give you the same total contribution to reducing the uncertainty of y. Maybe if we do a picture of it, it would be, here's y. This is the total uncertainty in y. And here is x1, x2, x3, x4, x5, x6, x7. They could be overlapping, underlapping, overlapping each other. They could be anywhere. But after you know the values of all the x's, what you're left with is the background, the stuff that's not covered by the circles. And it doesn't matter in what order you apply the circles. Questions? Okay, let's talk a little bit about Markov sources. Until now, one of our stories for explaining entropy was that you have a black box, you push a button, you get an outcome. It could be a symbol, in the case of language, or it could be an outcome of flipping a coin or anything like that. And I said that every time you push the button, a new experiment happens, and that experiment is independent of anything that happened before. Another word for that, another term for this kind of setup is a memoryless source. It's a source of outcomes that has no memory. Namely, what happened to it before, what outcomes it produced before, does not affect the distribution of the outcomes that it will produce in the future. Another term for that is IID. You may see that in probability and statistics papers. IID stands for independent, identical and independently distributed. So every outcome comes from the same distribution and is independent of the outcomes that came before it. Now, memoryless source can also be called a zero-order Markov chain. And by just introducing this name, you can think of generalization. You can think of what the order 1 or first order Markov chain might look like. A first order Markov chain is a source. You push a button, you get an outcome. But the distribution from which that outcome came depends on the last outcome. but only on the last outcome, not on anything happened before then. So it's a memory, it's a source that has a memory of just one outcome, the last one. Only remembers the last thing that happened. So whereas for a zero order of Markov source, all you need is the distribution of possible values of, let's call it x, p of xi, I goes from 1, say, to n. Let's say there are n outcomes. For a first order Markov chain, you need to specify, or to fully define the particular first order Markov chain, you need to specify the distribution under each one of the possible conditions, which is under each one of the possible outcomes that last happened. So it would be specified as p of xi given p of x at, okay, let me write it a little bit differently. I want to introduce different notations. xt would be x produced at time t, and p of xt equals I is the probability that when you push the button at time t, or the tth time you push the button, you would get outcome I, and there are n possible outcomes. So for a first order Markov chain, we would need to specify the probability that xt equals I given that xt minus 1 equals some other value j, where both I and j go from 1 to n. Effectively, you have to specify n different distributions, one for each possible state in which the source is in. So you can imagine the source being in a state which is identical with the outcome of the last experiment. You push the button, it generates another outcome, or another symbol, from a distribution that's particular to this state, and then it switches to being in the state defined by the outcome that it generated. If you took automata theory, how many of you took automata theory? You might recognize a finite state machine or a finite automata here, except this is not a deterministic one. It's a stochastic one. In that course you probably discussed deterministic and non-deterministic ones. This is a generalization of both. Not only is it non-deterministic, but it follows a particular stochastic distributions, where non-deterministic in that course typically means you should consider all the possibilities. Did they discuss probabilistic one? I don't know. But anyway, the idea here is that you have n states. You can put them, let's say, in a circle. Each point represents a state. And when you're in a given state, you have a particular distinct probability of generating any one of the other states, including the state itself. And when the button is pushed, you move to that state, and now you have a different distribution of moving from any one of to the others. In fact, there could be one state that's very selfish, where with probability 1 you stay here, and probability 0 you go out. So once you hit that state, you never leave. That could happen. The important thing is that the first order Markov chain is characterized by a set of n distributions rather than by a single distribution. Or you can take these n and put them together in one conditional distribution, which is what we did here. Now what would the second order Markov chain be? Yeah, it's a source that remembers the last two outcomes, and the distribution of the next outcome depends on these last two. And now you have not n distributions, but n squared distributions. And again, they can be written compactly as the probability of x sub t given x sub t minus 1 and x sub t minus 2. Now, why am I all of a sudden switching to this? Do you remember our discussion of the entropy of English? Remember that one of the assumptions we made there was that whether we were talking about characters or letters or words, we made the assumption that every word is generated independently of every other word, or every letter is generated independently of other letter. And I mentioned to you that I thought this was a brain-dead assumption. This is not how languages behave, right? So what we were doing effectively is modeling language as a memoryless source, or a zero-order Markov chain. Before that, we made an even worse assumption. Not only was it zero order, but it was also uniform. Remember we said that if every word is equally likely as any other word, there's a certain entropy. And then we said, okay, they're not equally likely. There is more likely, other words are less likely. That reduces the entropy, but we're still treating it as a zero-order Markov source. We can now go a step further and treat it as a first-order Markov source. So we can model the distribution of words conditioned on which word came before them. When we do that, we reduce the entropy of that model significantly. So the entropy of that model you have a stream of words. It's supposed to be natural language. Word 1, word 2, word 3, and so forth. Assuming zero order, we can define entropy of the random variable W as some pi log of 1 over pi. Pi means P of Wi. Log of P of Wi. That goes from 1 to 100,000. This is how we define the entropy per word. This is zero order. Now, first order, we will look at the quantity h at Wt given Wt minus 1. We will estimate the entropy, the conditional entropy of a word given the word before it. Now we can use what we learned in information theory to write this as the entropy of a word, independent of what came before it, minus the mutual information between word t and word t minus 1. So the amount by which we will reduce the entropy when we consider it first order rather than zero order is exactly the average mutual information between successive words in the language. And we know that average mutual information can never be negative. Which means that when you switch from a zero order model to a first order model, your first order model would always have lower, at least not higher, entropy. And if you estimate your parameters right, it should be at least as good a model, typically a better model of whatever it is that you're modeling. Now you can try a second order model. The entropy of that would be entropy of Wt conditioned on Wt minus 1, Wt minus 2. And again, we can break that down using the chain rule that we showed before. This looks terrible. The erasing is... Maybe I should use a computer. Should have a whiteboard here. We can break it down using the chain rule into the full entropy minus the information that the last word gives you about the next word minus information that the next to last word gives you about the last word, given that you already know the next to last word, and so forth. So indeed, people have built models like that, both at the character level and at the word level, and measured the entropy of these models as well as the entropy of English, and wait, I'll show you in a minute. And it turns out that the benefit you get by increasing the order of the model keeps going down. It's diminishing returns. But you still get benefit by considering the last 2 words, 3 words, 4 words. And if you ask a linguist whether it's fair to describe language as a process that the next word is determined fully by the last 3 or 4 words, they would think you're crazy. Because a linguist looks at the entire meaning of a sentence, entire meaning of a paragraph or a document, and so of course something that happened at the beginning of a document has a bearing on what's going to happen next, even if it's separated by 100 words. And they would be right. But from an information theory point of view, that contribution is actually very small. And if you're trying to estimate the true entropy of English, you get very close to it by considering just the last 3 or 4 words. If you remember, Shannon was playing these kind of games. Now you will find this problem in many other real-world machine learning problems. When there's a certain uncertainty in the outcome, and you're trying to collect lots of predictors, and each one of them looks very promising, some more than others, and as you incorporate them into your model, their additional marginal contribution is smaller and smaller.
So how do you know that you are getting closer to the true entropy if you don't really know what is the true entropy?
So somebody asked me at the last lecture, how is the lower bound on the entropy of English achieved? And I didn't remember it then, and I still don't remember it now. But if you keep asking, I will go back and look at the paper. I think it's a very good question. How do you establish lower bound of entropy? It's not as obvious as how you establish an upper bound. If you look at the slides, what you'll find is if you go through this process with characters and you calculate the number of bits per character, if you remember, we started with 4.75 bits for a uniform distribution over all characters, IID, 0 order. And then when we converted it to still 0 order but not uniform, it went down to 4.05. And then if you introduce a first order Markov chain or Markov model of characters, you're down to 3.3 bits. Second order, you're down to 3.1 bits. And if you introduce words, if you remember, we were down to 1.75. And if you introduce second order words, we're down even below that. I can tell you that the best models that we've ever built for general English I would say about 1.2 bits per character. Now you might ask yourself, why in the world would someone devote several years of their life, as I have done, to building models that reduce the number of bits in predicting language? And the answer is actually these models have a lot of uses in language technologies. They are at the heart of speech recognition and machine translation and information retrieval and document classification and all the things that Google does for you and that others do for you. They all have statistical language models at the heart of them, and the better the model, the lower the entropy of the model, the better a job it will do. So there is actually value in shaving off these bits. Okay, I've actually jumped ahead already and talked to you about the general problem of modeling an unknown source. I used the example of language. The exact same story holds for any other sort of natural phenomena that you're trying to model. Let's say vision. Some of you are interested in vision. What's common to these situations is that you have examples coming at you from a source that you don't know. Unlike probability theory, when you start by defining the distribution that generates events, we don't really fundamentally know what the distribution that generates the events are. We can estimate it, as in the case of language, but we don't really know what it is. And we will never know if we really hit it, if we really got it right. So let's call this unknown distribution D, or P sub D, of a random variable y, what is the entropy of P sub D? The answer is we don't know, because the definition of the entropy of P sub D is sum P sub D of yi, or let's say y, times log 1 over P sub D of y over all possible values of y. And we cannot calculate this because we don't know the actual value for all the y's. So what do we do instead? We build an approximate model, like we did for language. So we call it the distribution that based on that model P sub m. M for model, D for, say, data or distribution or reality or whatever. Maybe it shouldn't be D, it should be real, R. Now, different people or different research groups build different models. So you are in research group 1 and you build PM sub 1, P sub M1, and your friend is in PM sub 2. And you're both sure that your model is better. How can you tell which model is better? Is there an objective way, since you don't know the truth, you don't know P sub D? The only thing you have is examples drawn from P sub D. So this is actually worth thinking about for another minute. You don't have the actual explicit form of the distribution you're after. But you have examples that you are told were drawn from that distribution. That's very important. The examples were drawn exactly from the distribution you're interested in. But you don't have in your hand an analytical formula for that distribution. You do have the ability to push a button and get another example from that distribution. Now you have two models, each one claiming to be better than the next, better than the other. How can you tell which model is better? Please, can you give me your name? Andrew. Can you example the entropy of the example data? How would you define the entropy of the example data? So entropy is of a distribution. Yes. So I take it to mean that you look at the example data and you look at what's called the empirical distribution of the data. The empirical distribution of the data is a distribution defined by the finite number of examples you have. Okay? So if I flip a coin 5 times and I got 2 heads and 3 tails, the empirical distribution is head, 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 tail, tail. That means 0.6 head and 0.4 tail. That would be the empirical distribution of my data. And then I can calculate the entropy of that. Is that what you meant?
Yes.
Okay. You could do that, sure. Was that a question or a suggestion?
Suggestion.
Okay, so I do that and then what?
Should be who's ever lower compared to that empirical distribution, right?
What do you mean by that? Who's lower compared to that empirical distribution? I can calculate, okay, so let me make a distinction between curly D, which is the true distribution, which I don't know, and regular D, which would be my actual data. D is a set of data, and P sub regular D would be the empirical distribution of the data. So P sub D is not the same as P sub curly D. Because when you draw from a distribution, you don't get an exact representation of all the possible outcomes in the right proportions. I mean, there are fluctuations. For one thing, your sample is finite. If there are 1 million possible outcomes and you sampled 1,000 times, you just got 1,000 representatives, that's all. So the distribution here could be very different. But it is related to curly D in that it was drawn from it. So In the simple case of a coin, let's say curly D is the true probability of head, and let's say that's 0.7. I flip the coin 9 times, I'm not going to get 70% head. There's no way I can get 70% head because 70% of 9 is not a whole number. I'm going to get some other numbers, but they're going to be related to the fact that the true probability is 0.7, right? So I have curly D, I have regular D, which is an empirical distribution, and now, Andrew, your suggestion is that I calculate the entropy of regular D, and what do I do with it?
Can't you just compare how surprised the models are on average over the data set?
Can you compare how surprised the models are on average over the data set? You could do that. Do you want me to do that? Is that a good idea? Yes.
You can calculate for T regular D times log of 1 over. So what's predicted by model 1 is placed as a log, and then you do it again for the model 6, and then you calculate the probability trend to that.
Okay, so I think I hear you saying the same things.
Oh, okay.
But correct me if I'm wrong. You're saying research team 2 and research team 1, they get the same data that was drawn from curly D, and they measure the amount of surprise on it. Research team 2 is surprised by log of 1 over P M2 of whatever the data is. So call it DI, data element I. And then you sum it over all the data elements. This is the sum of the surprise. And you do the same thing here. Log of 1 over P M1 of DI. I goes from 1 to N. You're comparing how surprised they are on average. So the idea is that at any one particular data point, one of them might be less surprised than the other, and then the next one will be the other way around. You cannot judge by a single data point. But the idea is that, oops, thank you. The idea is that if you do it over a large enough set, you get a stable picture that says, who's more surprised on average. Your assignment, should you choose to accept it, is to take this and understand it in terms of cross entropy, as defined in the slides. We'll go back over it next time we meet.